Welcome to our module on corrosion engineering, where we explore how materials degrade and what we can do to protect them. In this presentation, we'll look at the science behind corrosion, practical prevention techniques, monitoring methods, real-world challenges, and case studies that illustrate successful management strategies. Let's get started with a clear view of why corrosion matters in engineering and infrastructure. This slide outlines the path we'll follow. A concise introduction to corrosion engineering, the scientific fundamentals, practical prevention techniques, monitoring and testing approaches, the main management challenges, and a set of case studies that bring these ideas to life. Think of this as our roadmap, so you know when we'll dive into theory, hands-on methods, and real-world examples. Now we begin with an introduction to corrosion engineering, which sets the scene for why this discipline matters. We'll define what corrosion is, who deals with it, and how engineers approach preserving material performance and safety. This section gives a broad perspective on the field, so you can see the connection between lab principles and on-the-ground asset protection. Corrosion engineering is about preserving structural integrity, extending service life, and ensuring safety. In practice, that means choosing the right materials, applying protective systems, and planning inspections so bridges, pipelines, and industrial plants remain reliable. Effective corrosion strategies cut repair costs and prevent hazardous failures, so understanding the core purpose helps prioritize where prevention and monitoring should be applied. When we talk about types of corrosion, it helps to picture four common patterns. Uniform corrosion gradually thins a surface from widespread exposure. Pitting creates small but dangerous holes. Galvanic corrosion arises when dissimilar metals interact electrically, and stress corrosion cracking combines mechanical strain with corrosive environments to produce sudden failures. Recognizing these forms guides the right prevention and inspection choices. Corrosion has significant economic and environmental consequences. It drives repair and replacement costs, harms ecosystems through corroded material runoff and waste, and shortens equipment lifespan if not managed. Effective corrosion control reduces total cost of ownership, lowers environmental impact by reducing waste, and improves long-term reliability, which is crucial for both private industry and public infrastructure. Next, we move into the fundamentals of corrosion science to understand what drives material degradation. This section explains the basic reactions and environmental factors that cause metals to corrode, providing the scientific foundation you'll need to make informed decisions about materials, protective systems, and testing methods later in the course. At the electrochemical core of corrosion are anodic and cathodic reactions where metal atoms lose electrons and form ions, driven by redox processes. Environmental factors like oxygen, moisture, salts, and temperature influence these reactions and accelerate degradation. Visuals here highlight how small local differences in chemistry set off larger corrosion processes, so controlling the environment is often as important as material choice. Common corrosion mechanisms include oxidation-reduction reactions, where metal reacts with oxygen, galvanic corrosion, when dissimilar metals are electrically connected in an electrolyte, and stress corrosion, cracking from combined mechanical stress and corrosive environments. Each mechanism has distinct signatures and failure modes, so identifying which is active helps target the right mitigation and inspection strategy. Several factors influence corrosion rates and patterns. The intrinsic properties of the material such as composition and microstructure, environmental conditions like oxygen levels, moisture, temperature and corrosive agents, and electrochemical interactions, driven by potential differences between surfaces. Considering all three areas together is essential for accurate risk assessment and effective prevention design. Now we shift to techniques for corrosion prevention, focusing on design choices and protective technologies that engineers use to reduce risk. This section introduces material selection, surface treatments, cathodic and anodic protection, and integrated approaches that combine several methods for robust performance in different service environments. Good material selection and thoughtful design are the first lines of defense against corrosion. Evaluate the service environment. Choose materials resistant to expected conditions, minimize crevices and stress concentrators in the design, and plan for protective coatings or treatments where needed. These steps reduce maintenance burdens and extend component life when done early in the design process. Surface coatings and treatments act as barriers between the material and the environment. Common approaches include paints, resins, or polymer coatings, hot dip galvanization to add a sacrificial zinc layer, and thermal spray coatings that deposit metallic or ceramic layers. As shown here, selecting the right coating and application method depends on service conditions and expected mechanical wear. Cathodic and anodic protection are electrochemical strategies to control corrosion. Cathodic protection protects a metal by making it the cathode, often using sacrificial anodes or impressed current systems, while anodic protection applies a controlled potential to reduce oxidation in specific environments. Often, a combined or tailored approach offers the best protection for complex industrial systems. Next, we'll cover corrosion monitoring and testing methods that help detect problems early and verify protective measures. This section looks at non-destructive testing, electrochemical techniques, and visual inspection methods that together form a comprehensive condition assessment program for materials and structures. Non-destructive testing techniques such as ultrasonic testing, radiographic inspection, and magnetic particle testing let engineers detect internal flaws, measure remaining thickness, and reveal surface or near-surface discontinuities without harming the component. These methods are widely used in routine inspections and reliability programs to find damage early and prioritize repairs based on evidence rather than guesswork. Electrochemical testing provides quantitative measures of corrosion behavior and coating performance. Potentiodynamic polarization reveals corrosion tendencies. Linear polarization resistance offers quick corrosion rate estimates. Electrochemical impedance spectroscopy evaluates coating resistance over frequency, and galvanic testing assesses compatibility between different metals. Together, these methods guide material selection and predict degradation risks in specific environments. Visual and microscopic inspection remains a crucial step in corrosion assessment because it detects visible abnormalities like cracks, pitting, and coating failure, while microscopy reveals early-stage microstructural changes. Regular inspections feed into quality assurance and maintenance planning, ensuring that localized problems are caught before they become major failures. Now we'll discuss the major challenges in corrosion management, where science, materials, and practical constraints intersect. This part highlights extreme environments, new material vulnerabilities, and the difficulties of maintaining aging infrastructure, all of which complicate prevention and monitoring efforts. Extreme conditions accelerate corrosion and demand specialized solutions. High temperatures, speed oxidation, and material breakdown. Marine environments with saltwater promote aggressive galvanic and crevice corrosion, and chemical exposure from acids or alkalis can rapidly damage surfaces. Each scenario requires tailored materials, coatings, and maintenance regimes to remain effective under harsh service conditions. Advanced materials bring performance benefits, but also new degradation modes. Composites can suffer microstructural damage from UV or environmental stress. High-performance alloys used in aerospace may still corrode under chloride exposure or prolonged stress, and additive manufacturing can produce uneven microstructures that are prone to localized corrosion or stress cracking, all of which call for dedicated testing and monitoring. Aging infrastructure presents a complex set of problems. Structural weakening from years of corrosion, inspection gaps where traditional methods miss early signs in hard-to-reach areas, and repair challenges when retrofitting corrosion-resistant technologies into existing systems. Addressing these issues requires prioritized inspections, cost-effective retrofits, and long-term planning to extend service life safely. Finally, we'll look at case studies that show how theory and methods come together in practice, illustrating pipeline protection, marine corrosion control, and aerospace strategies. These examples highlight the decisions, trade-offs, and monitoring approaches that demonstrate successful corrosion management in different industries. Our first case study focuses on pipeline corrosion management, where external coatings and cathodic protection prevent moisture and soil-borne corrosion, but pipelines under stress can still be vulnerable to stress corrosion cracking. Implementing smart sensors and real-time monitoring helps detect and localize corrosion early, enabling targeted maintenance before failures occur. The second case study examines marine environments where high chloride levels accelerate corrosion. Effective strategies include using corrosion-resistant alloys like stainless steels, applying specialized anti-fouling and protective coatings to hulls and structures, and deploying sacrificial zinc or aluminum anodes for cathodic protection on ships and offshore platforms. In aerospace applications, corrosion control relies on careful material selection, such as titanium or aluminum lithium alloys, surface treatments like anodizing or thermal spray coatings, and strict environmental controls during storage and operation. These measures, combined with regular monitoring, reduce the risk of localized corrosion that could compromise critical components. Thanks for watching this overview of corrosion engineering. We've covered fundamentals, prevention techniques, monitoring methods, challenges, and practical case studies to help you apply these concepts. If you'd like a deeper dive into any section or practical checklists for inspection and maintenance, let me know, and we can continue with targeted resources and examples.